this lecture about rendering accessories. By accessories, I mean things that are important but don't really fit into any of the other lectures. We will start with a bit of sampling theory and learn how to use filtering to prevent aliasing. Next, we'll talk about parallelization and how to deal with filtering in practice. Post-processing is at the end of the rendering pipeline. We will learn about how to map the high dynamic range data to computer displays and files. Then we'll have to talk about measuring error a bit. And last but not least, we'll take a step back and see how to reduce error by using more uniform samples. Let's start with sampling theory and filtering, the goal of which is to reduce or prevent sampling artifacts, or in other words, aliasing. By the way, that picture is from Finland, the home of some very good computer graphics people. We begin with an example. On the left, filtering was used, on the right, not. The left looks a bit better when you compare over here and also here at the bottom. But we can zoom in to see the difference more clearly. There are these bright pixels in high frequency areas that clearly go away when we filter. We have to look into it. Let me give some context about where filtering happens. It is applied in the image coordinate system where we see the pixels. That means that it lives in the main rendering loop where we walk over pixels, in contrast to how we lived in the first part of the path tracing lecture, the recursive part. Okay, we are in the main rendering loop where we go over all pixels and the number of samples n, create a camera ray and start tracing it. Until now, we shot every pixel contribution ray through the center, but this is just an arbitrary choice. The underlying integral and code works for all floating point positions within the pixel plane. Next, we'll forget about one of the screen dimensions and start to think about a 1D function, f of x. This is to make the explanation easier. All of the results also apply to the 2D screen we have in rendering. The green wavy line is now the function that we want to sample and reconstruct as pixels on the screen. Here you see the path integral formulation of light transport because it's shorter. It's the integral of the light transport function f of j over all transport paths. You already learned in the first part of this lecture how to estimate the result using Monte Carlo. It's the same process, no matter the notation. But we can also use the recursive formulation. In that case, we would say that we have a function f that eats screen coordinates. The definition of the function tells to shoot a ray through that position and compute the light recursively. That recursive computation returns the brightness at that position of the screen. Until now, it was always the pixel center, but it's valid for all screen positions. For now, we assume that f of x is a continuous function, as opposed to a stochastic variable like in Monte Carlo integration. That means that it always returns the same value for a given position, and positions are not discrete like monitor pixels. Now, we have that function, f of x, but only discrete pixels like you see here, where each of them can display a single value. This is a sampling problem, very much like when you have to convert an analog audio signal to a digital one and then play it. Let's say we go the simple and naive way and sample the signal at the centers of the pixels. After sampling, we have to reconstruct the signal, that is, draw it on the screen. As said, every pixel can have only one value, hence the boxy reconstruction. This gives us a faithful representation of f if the frequency is low, like here on the left side. By faithful, I mean that the pixel values are close to the signal f and that they would not change much if we shift the sample position by a tiny bit. That means less than a pixel. So sampling the pixel centers works if the signal f has a low frequency, but it breaks down when the frequency becomes too large, like over here. The problem is called aliasing. You probably already heard about it. It happens when the sampling frequency is below the Nyquist frequency, which is 2x the signal frequency. There are two solutions: increase the sampling frequency or smooth the signal. We can't really do the first because it would change the rendering resolution. Besides, when would we stop? But we can smooth the signal. Smoothing the signal means to apply a low-pass filter H. We are filtering out high frequencies, hence the name of this section. Look at that. If we sample the function f of x convolved with h of x, which is shown over here, at the centers of the pixels, it will give us a faithful representation of the function. You might think that we lose data, but that is not really the case, as we couldn't reproduce it anyways. Let's look now into the choices for the filter or convolution kernel H. But first, let's look at the properties that we need. It should integrate to 1. This is because f of x convolved with h of x should not be brighter or darker than the original signal f. This is more of a theoretical constraint, as any convolution kernel can be scaled, and in fact we do that as part of the equation that we use. Obviously, the kernel shouldn't be too small or too large. In the first case, we wouldn't fix the reconstruction problem, or in the second case, we would lose too much details. And finally, we need a good shape. Depending on the shape, some artifacts might appear. Different shapes can create different artifacts, and it's generally a trade-off between these artifacts. But we won't go into much detail there, because we would need much more sampling and reconstruction theory, including the Fourier transform. Here we see some choices for the kernel. The first row is the 1D case and the cross-section through the center of the 2D case at the same time. The simplest is the box filter. You just take the average of all pixel samples. Don't worry, we will talk more about implementation later. It is common in super simple renderers, in case the author is too lazy to implement something better. It allows high frequency sample data to leak into the reconstruction. And a reference for that is our course book, PBR chapter 7.8.1. The tent filter is slightly better, and the Gaussian filter is reasonably good, but smooths the result. Did you see that it is clamped over here and here? This is to limit its support. There is a family of filters called Mitchell-Netrevally. You can see that they can be negative over here and here. This sharpens the result somewhat, but it can cause artifacts called ringing, which depends on the parameters. The Mitchell-Netrevally filter is considered the best by some, and I think it's a bonus task in one of the assignments. Anyway, we will not go into further details. In my opinion, the differences between the Gaussian and the Mitchell-Netrevally filters are minute, so it doesn't matter that much. Okay, we have seen why we have seen the filters, but not how that works in the context of rendering. So here we go. You see the signal f and the filter kernel over here. Before we said that we compute the convolution between f and h in order to get a smooth signal. But we do not have the signal f as a function, we can only sample it. And so we need to change the approach somewhat. We see that the center of the filter kernel is placed over the center of the pixel. This is like we wanted to compute the value of f convolved with h on that position. And that makes sense, because we later want to reconstruct f of x by sampling f convolved with x at the pixel center. And now we take samples of f times that shifted kernel h. Samples close to the center of the pixel will have a large kernel weight and therefore a larger contribution to the pixel value. Here you see the equation for that process. In the numerator over here you see exactly what we said before. The sample value of f is multiplied with the value of the kernel centered at the pixel we want. This is exactly the same term as inside the integral of the convolution. And so this whole thing represents h convolved with f. Remember that we said that h should integrate to 1. So in theory we should use n over here instead of the sum. The sum results in n on average. However, using the formula as it is reduces noise. And here you see the equation for the two decays that we actually have in case of rendering. It works the exact same way. Now, let's have a graphical view of the kernel again. The green circle is the filter, and the red dots are the samples for the current pixels. The filter is larger than the current pixel. And so pixel samples also contribute to neighboring pixels, like these to the left pixel and these here to the right pixel. And the same for all pixels around this center pixel. Okay, I hope that is more or less clear and we are ready to look at another thing concerning filters. Many discrete smoothing filters are separable. That means that the matrix of the filter, like here the 3×3 matrix, used for filtering can be produced from the outer product of two vectors over here. This applies, for instance, to the Gaussian, tent, box and Mitchell-Netravalle filters. And since these filters are symmetric, the two vectors have the same values. Separability allows us to implement filtering more efficiently, as we need to store only one vector instead of the whole matrix. The filter values can be computed on the fly. In case you work on the last assignment at TU Wien, this is the code that you have to complete. Alright, we learned that filtering fixes aliasing problems. Low-pass filters are used and the process includes convolution and normalization. Most filters are larger than a single pixel, and so most samples affect more than a single pixel. Here are some reading links. Check for instance our course book. It covers sampling and reconstruction quite extensively, including more sampling theory and comparisons between the different filter types. A classic read is "A pixel is not a little square." You can also read the original paper by Mitchell and Netravalle. And finally, I've seen that there are many YouTube videos about sampling theory and even more text resources on the net. That concludes our section about sampling theory and filtering, although we'll see it again in the next section. Filtering prevents or at least reduces sampling artifacts by low passing the image signal and then sampling in the pixel centers. These samples are then used as the pixel color. And now let's have a quick look at parallelization. The goal is clearly to harvest the performance of modern multi-core systems. That is already crucial today, but it becomes more and more important as the core counts increase. By the way, if you read papers from the 90s, that won't be the case. Oh, and this picture is also from Finland. They have a lot of amazing lakes and forests, and summer at a cabin is super relaxing. Monte Carlo rendering is embarrassingly parallel, as every sample of the integrand is independent. We are talking about the path that starts or ends at the camera, not the hemisphere samples, although these would be independent as well. So we could start a new thread for each sample, for each path that starts at the camera. But that would require synchronization at the sum and probably unneeded overhead for threading. That might pay off for GPUs, but probably not even that. Certainly not for CPUs. We could start a new thread per pixel, more like GPU style. For the CPU, that is still too much overhead. Plus, we would actually need synchronization because of overlapping pixel filters, but that is doable. So for CPUs, we use blocks of pixels. Such blocks can have a size of, for instance, 32 times 32 pixels. Another advantage is that the first few bounces will have a high probability of hitting the same geometry, and so the caches of the CPU have fewer misses. Blocks at the border of the image are often smaller, like over here and here. Samples are taken for all pixels inside a block. But as said, due to filtering, each sample can contribute to more than one pixel, including pixels outside the block. Therefore, each block needs an additional border to store that contribution. And so, when a block is handed to a thread, it must be slightly larger than the extent of the sampling area. This means that blocks can overlap. We will now see how that is handled in a rendering system, like Nori. When we look back at the equation for filtering, we see that there is a sum in the numerator and a sum in the denominator. We have to complete the sum before the division. That means that we need to do the division after merging the blocks to the complete image. And that is actually quite easy. We just keep track of the numerator and the denominator separately. We add the blocks to the final image using blocking or atomic add operations and do the division once all threads are finished. Nori solves that by putting the three values of the numerator for the three colors and the filtering weight into a 4-element vector. The blocking add operation doesn't even need to know what the data is. As a last step, we simply divide all pixels by their fourth component. For path tracing, we can use this method without any problems, but some other algorithms require access to the whole image. For instance, that would be the case if we started tracing from the light sources and wouldn't know which pixel the ray ends up. Rendering is very easy to parallelize, even to multiple machines. This works by computing multiple images with different random seeds. They can be added up after finishing rendering using 32-bit floating point image formats. That way, I occupied several thousand CPUs on a cluster and more than a terabyte of RAM during my master thesis at Aalto, Finland. Some bottlenecks start to appear once your scenes become very large, for instance in large film productions. Sometimes the scenes don't even fit into RAM anymore and special architectures need to be employed. That was a short section about parallelization. Many renderers implement threading by rendering in blocks. These blocks need to include a small border to account for filtering, and it is relatively easy to parallelize even to multiple machines. This is my cherry tree in Poland, and we will talk about post-processing now. That is, what we do before storing or showing our computed radiance values. Let's start with a bit of context. The first thing to realize is that the dynamic range of light in the real world is considerably larger than what we can show on displays or store in normal image files. Take for instance the difference between illuminating a piece of black and white paper by the sun versus the moon. The sun's illumination is 8 million times stronger. The human vision system can adapt and process a difference of up to 100 million. Adaptation takes some time, but still. In technology, displays can have a difference between the brightest and darkest pixel in the ballpark of thousands. Modern displays that can partly dim the backlight can do more, but that requires special drivers and especially authored content. The default are 8 bits per color. Image formats with 256 levels of brightness seems almost archaic, but that's the deal for most cases. Our computations during the light simulation use 32-bit float. The range is large enough. So, tone mapping is about reducing the dynamic range from our light simulation to a 0-1 range that can then be mapped to an 8-bit integer. We need to compress the range. And on a side note, there are 10 or even 12-bit displays today, but these require different processing that probably happens in special software or in the driver anyway, and we will not cover it. It is easy to output 16 or 32 linear float data for that purpose. Let's take this image as an example. It is tone mapped in some way, otherwise we would not see it. For the sake of the argument, let's assume that right here in the light, it has a brightness of 35.5. That's a float value that could arise from rendering. On the white piece of paper over here, it could have a brightness of, say, 1.2. And somewhere in the dark over here, it could be 0.1. How can we map these values to a range from 0 to 1 so that we can then convert it to 8-bit? One option could be to divide by the largest brightness value. That is a valid method, and don't laugh, I used it at some point in time. If the scene has a low dynamic range, that is pretty okay. But it's certainly not a good method in terms of quality and stability. Our next attempt could be to clamp the image to a range of between 0 and 1. That is what often happens before tone mapping is implemented. With most scenes, that is not that bad either. Taking the logarithm is a very basic tone mapper. I used it to display some scientific data in another domain. Simple, but not really proper. We would want to adjust the parameters, give more light to shadows, etc. And right here we now have a proper tone mapper, Reinhardt. Before we continue, let me say that there are global and local tone mapping algorithms. The global ones apply the same function to all pixels, while the local ones are applying different parameterizations depending on the local neighborhood of a pixel. So for each pixel they look at the neighborhood and then they compute a new parameterization and apply the tone mapper. Accordingly, the local ones are slower, but they can retain more details. We will see an example in 2 slides. The Reinhardt tone mapper is widely used and there is a global and local variant. We will not cover the processing steps, it would be tedious and you would have to look them up when you implement anyway. Refer to the paper. The goal of that process is to find a transfer function, like shown here. The exact shape of that function depends on the whole image in case of the global variant and on the local neighborhood in the case of the local variant. The shape is somewhat similar to a logarithm, hence logarithms are also usable. Here are the examples that I promised. On the left you see a global mapping and on the right a local one. If you look closely, you can see that some of the darker areas on the right are darker, like here and also here. The window over here is blurred a bit more compared to here. Blurred. There is some sort of bloom. It's not as crisp as on the right. Let's zoom in a bit. The global version is less crisp. Look at here and here, or also here. The local contrasts are larger in the local version. However, what can happen is that, for instance, parts in this light over here are brighter than parts on the floor, which is unrealistic. Reinhardt is not the only tone mapper. Here is a reading list, but there are more on Wikipedia. Enough of tone mappers. Let's turn our attention to gamma encoding, something slightly different. Human perception of brightness follows an approximate power function. We have greater sensitivity to relative differences between darker tones. Therefore, gamma encoding is used to optimize the usage of bits when storing or transmitting an image. It's applied after tone mapping, simply I, which is the image to the power of 1 over 2.2. Check online resources for more information. You might need to decode gamma when reading textures. Most image formats store gamma encoded, but light simulation needs linear intensities. Okay, to sum up, tone mapping is used to map from HDR, which we used during the simulation, to a 0 to 1 floating point format, and gamma encoding is used for storage. All of that is not needed when we use HDR formats, like 16 or 32 bits per color channel. The next topic is measuring error. And I know that it is a bit boring, but it's important nonetheless. It is crucial to be able to compare algorithms, but we can do even more, as we will see. The picture shows a former eucalyptus forest in Australia. The error there was to put koalas in the trees. Too many koalas, too few trees, and of the wrong type. So estimators, well, they estimate values. For instance, the color of a pixel. As such, they don't give the real value, and therefore there is a certain error. In rendering, in my opinion, it's most useful to compute the error before post-processing, and that's also what we use here. Estimators are denoted with a hat. That is a general statistician thing, and the error can be computed as the estimate minus the real value. That is the absolute error, as opposed to the relative error, which you can see over here. So divided by the real value. This error also contains a sign. Sometimes the unsigned error or amplitude error is computed. The nomenclature is fuzzy, and this one is sometimes also called absolute error. When we want to compute the error for the whole image, we can take the mean of all errors. But in that case, we have to compute the amplitude error, or better, square of the error, otherwise the positive and negative errors would cancel out. The real value I is usually not available, therefore high quality reference images, also called ground truth, are used. We will now see some examples of such error. On the left you see a high quality reference, and on the right the absolute error of a path traced algorithm. In here you can get an idea of the difference between absolute and relative error. The error shown is the standard deviation per pixel. That is something that we will get into in the next few slides, but you can see the differences anyways. In the first example on the left, it seems at first that the relative error is better, because in very bright areas we won't see the error anyways, like here in the window. But on the example on the right, we can see that the error can become very large in dark areas. One could say it explodes. In fact, it's needed to add an epsilon to the reference so that it doesn't produce nulls or not the numbers. But enough of that. Let's now look at classes of estimators. On the right, you see plots of signed error. That is I hat minus I against the number of samples on the x-axis. You won't see such plots in papers or websites, as other error measures are used most of the time. But they are good for visualizing the concept here. Unbiased estimators, like for instance Monte Carlo integration methods, have the expectation of the estimator equal to the true value. The error plot of a single estimator oscillates around 0, and the amplitudes become smaller as n increases. Biased but consistent estimators at no point have the expectation of the true result, but the error becomes smaller with larger sample sizes. The estimator converges to the ground truth. The error can be negative as well. This here is just an example. And finally, there are biased algorithms that never converge to the true solution. That usually happens when you trade noise for bias. You can get a nicer picture with less noise that doesn't match the physics of light, for instance. A typical example would be clamping the contribution, which means clamping the files that you probably saw in the path tracing assignments, limiting the recursion depth, or just not rendering certain effects, like for instance caustics. We are focusing on unbiased Monte Carlo integration, and at this point I would like to make a super brief recap. I is the integral of f over a certain domain D. We can multiply f by p over p and turn that into an expectation using a sampling strategy that creates samples according to the PDF of p. That is not an estimator, as we have no procedure for estimation yet. We can use the law of large numbers to turn that into an estimator. The law of large numbers tells us that the average of an ever-increasing number of samples of x is the expectation. When we apply that to our stochastic variable f over p, we get the Monte Carlo estimator over here. Now we need another super short recap about probability and the variance in particular. The variance of a stochastic variable gives us a measure of how far spread out the samples will be, and you see two equivalent methods to compute it over here. The next result tells us how the variance of a constant times the sum of uncorrelated variables is computed. The constant a can be moved out like over here. And the variance of a sum is the same as the sum of the variances. These equations are taken from Wikipedia, and I think you already saw them in this lecture. Finally, the central limit theorem. It is usually written in a slightly different way, but this form is equivalent and more useful to us. The average of a ever-increasing number of samples of a given stochastic variable x tends towards a normal distribution with the given parameters. I've put the CLT and our estimator next to each other. We see that the estimator is pretty close to the CLT, with the stochastic variable being f over p. That means that in the limit our estimator I hat is a stochastic variable and becomes normally distributed. Now let's look at the error I hat minus I. We know that the expectation of I hat is I, so we can substitute it. Now we quickly see that the expectation of the error is 0. That's logical since it's unbiased, and that's what we already saw in the Monte Carlo lecture. We can also look at the variance of the error. We saw that the variance of a sum of stochastic variables is the sum of variances, so when you compute the variance of the error, we can just fill in and we get this one. The variance of an expectation, which is a constant, is 0. Therefore, we are left with the variance of the error equals the variance of the estimator. And finally, without steps, the distribution of the error also tends towards a normal distribution. You should be able to check that without problems on your own. Okay, the variance of the estimator is important. What can we find out about it? On top, again, the estimator, denoted with an hat. And as said, the estimator is a stochastic process. Therefore, the result is a stochastic variable again. We can compute the variance of that estimator. The result will tell us how far spread out the estimates will be. In other words, if we run the estimator several times, how far will the results of these estimator runs will land apart from each other. At the same time, since the variance of the estimator equals the variance of the error, it also tells us how far spread out the errors will be, how large the errors will be on average. Using the equations from the probability primer before, we can pull out the 1 over n, it'll become 1 over n squared, and make it the sum of variances. Now, the variance of f over p is a constant. It's a theoretical value, we don't know it, but we know that it exists. And the sum of n values is n times the value. So we can replace the sum by a multiplication with n, and 2 of the n cancel out. So the result here is that the variance of the estimator and the error is 1 over n times the variance of a single sample. Neat. To summarize, the distribution of error of a Monte Carlo estimator tends towards a normal distribution as n increases. Its expectation is 0, yes, because it's unbiased. The variance of the estimator is also the variance of the error. And finally, the variance is in strict relation with the number of samples. Double the n will result in half the variance. Variance, what do we know about it? Can we compute it somehow? We heard about importance sampling before, and we learned that it can be used to reduce the variance and the error. It would be even better with MIS. Can we compute the variance out of it? Well, no, we can't. Or at least I'm not aware of a method to do that. It's kinda a dead end. We can measure the sample variance. It's simple. You have a bunch of values, the f over p's, and compute the variance. In order to get an estimate of the estimator variance, we need to divide by n, so division by n squared in total. This process does not even require a reference solution. It is even possible to do that online, which means that we do not need to compute the average of all samples before we compute the variance. Search for the Welford algorithm. When we want to do that for path tracing, we would compute the per pixel variance. Time for some examples. On the left, you see a rendering of a bathroom scene. On the right, there is the standard deviation per pixel. In my opinion, standard deviation is preferable compared to variance because it is linear and the variance has a quadratic scaling. Here we see another example, and we can clearly identify that the caustic is problematic for the path tracing algorithm because the standard deviation or variance is high. Alright, what can we do with this information? One thing would be, we know that the error in that area is large, but we also know that doubling the number of samples reduces the estimator variance by half. Right, so, throw more samples at these problematic areas. This is called adaptive sampling, and there are many methods to do that in an intelligent way, but that would be too much for this lecture. Look for papers on your own, please. Another method to combat noise in renderings is smoothing. Adaptive smoothing is used often, which means that edges are not blurred, for instance. Most noise reduction methods are biased, however, a little bit of bias is often better than a noisy image. If we know that there is a lot of error in a certain part, in other words, objectionable noise, we can apply more smoothing, specifically in these areas. This would prevent unnecessary smoothing of diffuse textures, for instance. And finally, we can compare different algorithms. On the left-hand side, we have path tracing. It contains a lot of error in the caustic, which is fixed by bidirectional path tracing. However, on bidirectional path tracing, it looks like there is more errors in the refractions inside the bottle. This is because bidirectional path tracing has fewer samples because one sample is more expensive, and therefore we simply have fewer samples in that bottle. So generally, if you develop a new algorithm, it is good to know its strengths and weaknesses. And this is a good method to do that. In my opinion, better than comparing ground truth to real images like we saw in the intro. Finally, we often want to rank algorithms, e.g. say that the algorithm A is better than B according to some metric. Literature often uses mean squared error to do that. That is a per pixel mean of the squared error between a rendering and a ground truth. There are many variations of that, for instance computing the error relative to the brightness of the reference like we saw at the beginning, or computing mean absolute error which weighs outliers less, or computing root mean square error which is linear like standard deviation. All these methods are sensitive to outliers, for instance fireflies in the case of path tracing. Over here you see the root mean square error plotted over rendering time. The jumps over here and here, these are outliers, and so it would be hard to choose a fair rendering time for comparison. So I'm advocating to use the root of mean variance, where the variance is estimated per pixel. Here are some reading links. The first one is a diploma thesis and the second one a paper. Both roughly cover the same methods, which also includes a plot of error over frequencies, but the first one is a bit more comprehensive. And here comes the summary slide. We have our mission accomplished. We know how to judge the quality of our rendering work. For unbiased algorithms like path tracing, that is simply measuring the variance or standard deviation. We can use that knowledge to throw more samples at problematic areas, smooth out noise in that areas, and for comparisons between algorithms and sampling strategies. And now our last topic for today: stratification and sampling patterns. I don't remember where I took that picture, probably somewhere in France. It's a facade, but it looks a bit like cosine hemisphere samples projected on the tangent plane. I like it. We are now making a jump from looking at the result of rendering back to something which is related to the basic concept of integration and its implementation. So sampling patterns are a detail of the Monte Carlo integration. So this is an addendum to the Monte Carlo and sampling lectures. It's a bit away from the other topics that we covered today. First, I'll explain the problem using a 1D example. Let's assume equidistant samples, which is basically a trapezoidal integration rule. This line on the right is the sum of these lines. So we just rotate all of these lines 90 degrees and we put them next to each other. Dividing the length of this line by the number of samples, which is 4 in this case, would give us the integral of the blue function. But since we are doing Monte Carlo, the samples will not be equidistant. Sometimes they will cluster in one of the areas, like in here they cluster on the left side. And sometimes they cluster on the other side, in here on the left, on the right, which gives us different results. This is variance that can't really be explained by looking at the probability densities. Both of the samplings use a uniform probability, but still the result is different. I mean, yes, you introduce variance by the fact that there is a PDF and sampling and everything, but that variance feels unnecessarily excessive. We want randomness, yes, but that is just too much. Obviously, I wouldn't bring this up without a solution. Let's divide the integration domain into n equidistant areas and take one random sample in each of these areas. Like here. This is called stratification or stratified samples. The samples are still random, but more regular. In practice, you would take more than one sample per region. We will see soon. When we compare the results, the stratified variant has smaller error. Here we have another example, but in 2D. We have random sampling in here and stratified sampling in here. And we can see that this one is more regular than here on top. And as said, in practice, you could fill up each of these cells with 2 or 3 or 4 or whatever number of samples. Okay, well, but let's think whether this can scale to 4, 6, 10 and more dimensions of a path space integral. The curse of dimensionality kicks in again. We can't have even one sample per grid cell for all of the grid cells. Same as with the trapezoidal rule, like in 10 or more dimensions. This would just explode. However, there is a simpler solution. From the cells with the least number of samples, pick one randomly and then sample in it. That way, the cells stay relatively balanced. The maximum difference for each sample per cell is 1. This approach should be implemented directly in the random number generator before using these numbers on BSDF samples, etc. So before any warping is applied. This way, the benefits translate to the warped distribution as well. So even when applying warping, the sampling will be more regular. This domain before the warping process is also called the primary sample domain. Low discrepancy series are a way to achieve uniform sampling without using stratification. Basically, the random number generator is replaced with an algorithm that generates samples according to a mathematical formula, guaranteeing a relatively uniform distribution at all sample counts. We kinda hack the random number generator to produce stratified samples. The numbers are not random, hence Monte Carlo turns into Quasi-Monte Carlo. The Halton sequence in the picture is one example for such an algorithm. The whole thing is a bit tricky to get right, best follow the course book, we have references at the end of this section. Quasi-Monte Carlo is often applied only to the first few dimensions of the integral, for example, the direction of the first bounce, surface samples of a light, etc. In fact, using the same number of samples per pixel is already stratification. Any of these methods become pointless in higher dimensions, because sampling will be very sparse. Whereas, in many scenes, most of the error is in higher dimensions. For example, caustics, deep refractions in glass, and so on. However, it's still used because it's cheap and diffused surfaces are cleaner. It's also a bit funny. Previously, we learned that the convergence rate of Monte Carlo is 1 over n. Using sampling patterns can be even better than 1 over n. That is, error in lower dimensions converges asymptotically quicker than in higher dimensions. That's similar to Simpson's and other higher order quadrature rules, which can also achieve faster convergence rates, but they also don't work for higher dimensions. And so here are the reading links. Check out our course book again. There is also a Ziggraph course and the paper by, I'd rather not pronounce these names, which shows a way to analyze sampling patterns and gives exact numbers on the convergence of certain patterns. That concludes our section about sampling patterns. We learned that having regular samples reduces error in low dimensions. And that's it for today. We covered a whole bunch of topics. Oh, and I wanted to include that image in my diploma thesis, but failed. It's a glass of water with an out string which shows participating media and a nice caustic. Thanks for your attention.